Yep.
Thank you, Professor Wilson. Hello, everyone. I'm Xiaosu from University of Washington. I'm currently a fourth-year PhD student. I'm presenting today my last year's internship work with Adobe Research, SonifyAR, context-aware sound generation in augmented reality. I'm presenting on behalf of my professor, John Furlick, and also my Adobe mentors, Unico and Chang Xiao. Sound is critical for how we perceive this world, which also applies to the AR world. Having a contextual sound is helpful for us to understand what is happening in AR. For example, the formulation of a molecule. The placement of virtual furniture into your living room. And also, the walking of a virtual robot on your desk and on the ground. However, creating such context-aware sound effects can be challenging for the AR creators. Firstly, the current creation workflow lacks the real-world context. For example, for this very specific simple example, we need 2 sound assets assigned to different materials. However, the existing authoring pipeline usually happens before the AR experience, so there's no access to this kind of environmental context at all. Secondly, existing AR authoring tools also have a limited list of AR interaction types that can be linked to these sounds. Thirdly, AR creators have very limited sound sources. They need to either look it up in local sound library or record it by themselves, which puts a great threshold or barrier for their creation. In this case, the existing AR sound interaction are mostly restricted to the virtuality of the AR content. However, the AR world contains more than just the virtual content. It also has 2 other key factors, the user and also the real-world environment. And this creates an even bigger AR sound interaction space. For example, between the user and the virtual content, when for example, the user taps on some virtual content. Between the virtual content with the real-world environment, for example, the little walking robot that stomps on your desk. And also between the user and the reality. For example, when the user taps on the real-world surface through the AR interface. And sometimes even involving all of these components, like when the user is holding some virtual contents and sliding it on the real-world surface. The existing tools usually just support a very limited subset of this interaction space. But in this work, we aim to expand it to the entire interaction space with our work, SonifyAR. We present SonifyAR, which is a context-aware AR sound authoring system. With SonifyAR, the AR creator performs the interaction in the AR space, and the context matching sound assets will be generated for them in real time. There are 3 key designs in our system. Firstly, we do context collection with programming by demonstration, which means all the user need to do is just whatever they want in the AR space, and the system will collect the information of the context for them. For example, for this user sliding a ceramic cup on the table example, when they do this, the SonifyAR system will collect the context information, including what are the virtual object of this interaction, what is the user doing, the event type, which is sliding on the desk, and also the real-world context information, which at this stage includes 2 main information types, the plane detection from ARKit, and also the material segmentation from Apple's DMS model. With all these information, potentially we can create very matching sound for this specific event. However, we still face the problem of how to holistically incorporate these information in this generation process. This leads us to the second key design of our system, which is using text as the medium for the context. We use a text template to incorporate all of these information, like what is the event type. This event is caused by the user. The event is casted on a ceramic cup. And also, everything happens onto a real-world wooden surface. With all these information collected, we can then use it to retrieve or generate the sound assets that match this specific event. However, these two different methods, either retrieve or either generate, have their own trade-off of performance. The retrieve-based methods usually have better quality, but it doesn't guarantee coverage for all the edge cases that could potentially happen in the AR interaction. The generate methods have better coverage and sometimes even great adaptability of the sound to the AR interaction, but sometimes the quality is subpar. In this case, a very natural thinking is just like, why not both? Why not do them together in parallel, and then we just choose the best one for every case we need? This leads us to the third key design of our system, which is using LLM for generation and retrieval. We use LLM to control all the generation and retrieval methods and generate all these assets for user to select in real time. Currently, we have 4 methods. Firstly, a local recommendation method, which takes in the context information and also a sound list provided by the user. The LLM will just recommend the best matching sound to this current context. For example, when the user taps on a ceramic cup and given a little list of their current sound library file names, the LLM will just recommend the top 5 file names. For example, this one. Is it heard? Louder. The second method is we can also do online retrieval with the context information. In this case, the LLM will generate a distilled context like as a simplified retrieval prompt so that it can be used to search for sounds on online libraries. For example, with a little toy airplane flying, we can send the context information to LLM and let it generate a simplified retrieval prompt. In this case, plane fly. Very simple. And then we use an online sound library called FreeSound to retrieve a potentially matching sound. The third method is text-to-sound generation, which utilizes a text-to-sound diffusion model to generate a potentially matching sound based on the context information. For example, when there is a dinosaur roaring in the AR space, the context information as a text can be parsed by the LLM and simplified into a generation prompt, dinosaur roars. And then the text-to-audio diffusion model, which currently we use a model called Audio LDM, by the way, can generate a sound roaring. Lastly, we have text-to-sound transfer method, which changes an existing sound asset slightly based on the context information to better fit this current AR context. For example, when we have 2 little metal balls hitting each other in the AR space, we can use the context information to send it to LLM. The LLM will generate a simplified transfer text prompt, which is metal balls collide in this case. We also feed an example asset, which is a general tapping sound. And then the audio diffusion model will generate a transferred AR sound to better match the metalness of this current event. Hear the difference? With all these 4 audio generation methods, we finished the entire end-to-end pipeline of the SonifyAR system, which starts from an AR event. And as the event happens, the system captures the context information of it, including the subject, object, and also environment information. turn it into a text template, and then use LLM to control all the 4 possible sound generation methods, either local or online retrieval, or text-to-sound generation, or transfer. Then we have a user interface, which is a popping up panel to list all of these sound assets for users to choose from. The user can just tap to test out any sound. Double tap to select it. Then it will be applied to the AR experience in real time. If they're not satisfied with the sound or want to make some changes, they can also use the interface to call out 2 more options. One of them is show more retrieval results, and another one is to continue using the text-to-sound transfer method. And then they can slightly change the sound based on their text prompt. And with the system, here are several examples of what are the sounds that the system can generate. Besides these pure entertaining examples, we also try to have some educational content. For example, this little physics experiment of momentum, like the ball slide down the slope and collide together. We can use our system to assign different colliding sounds of this physics process. And then the content becomes more realistic. We also see potential accessibility use cases for our system, because if we can assign different sounds to this kind of tapping, and also this kind of walking bands to different indoor surfaces based on their materials, the user can just better understand the surrounding environment without using the visual modality of the AR experience. Besides these applications that comes directly from our prototype, we also utilized our pipeline onto existing applications. For example, an existing poor dinosaur. Potentially, we can also apply it in the MR headsets. Like, for example, we can make the window slightly collide with the different surfaces and make a little sound to make people realize, okay, you're making the virtual and real world interface and context attack. You know what I mean. And lastly, we can apply it to existing AR authoring tool. This one is Apple's Reality Composer. We can let users just do their authoring process as they wish. And at the same time, we can also collect the context information and generate or retrieve the matching sound assets for them, so that to evaluate our system, we conducted a user study across 8 participants. We let them try out our user interface and the entire generation pipeline, and evaluate the general usefulness and usability of the tool. In general, we find very positive results of their user ratings, especially on the helpfulness of the pipeline, their willingness to use it in their own authoring practice, the improvement of immersiveness of the AR experience with the extra sound added, and also their preference over the automated pipeline over the manual one. The only potential improvement is in the sound quality from the diffusion models, which hopefully with the involvement of these models in the future will be better. This work have some limitations. For example, currently the LLM output is sometimes unstable, so that the text prompts used for the diffusion model or retrieval models are like missing the keywords in some cases. The sound quality can be improved, just as we discussed. And also, when the animation content of the AR virtual content is a little bit too complex, the audio content can mismatch the visual content in the keyframes. In the future work, we plan to merge this pipeline with other existing tools, for example, Unity Mars. We plan to keep expanding the environmental understanding thanks to all the recent VLM and so many other great models coming up. And also, we plan to implement some automated error handling mechanism, potentially with some sound quality judging model that helps us to filter away subpar sound quality from the diffusion model, or automatically regenerate when the result is not that perfect. Without these, I wrap up the talk and is willing to take questions. Thank you.
Thank you, Sha. So we're a little over time. Let's take time for one quick question. Can you make it quick?
Hi, Parastu from Princeton.
Hi.
Great work. I loved seeing all the different applications. I was wondering if you can talk a little bit about, this is great for the person who's building the AR experience, right?
Yes.
So how do you think you could extend this understanding to adapt the audio to the person who's experiencing the audio? So if I'm in a really crowded environment, or if there are children around, I might use a different, less maybe horrific sound effect.
Yeah, that's definitely true. So far, we built it for AR authoring use cases, so that we just throw all the possible generation results, and people can just do some manual choosing or filtering based on their needs. But in the case that you're referring to, either like the user are children, or like the people who doesn't want to do the filtering by themselves, or they expect the results in a real-time manner instead of in after some selection. I think it's definitely possible, since we can have some other models to do the automatic filtering and selection of these contents based on their user needs. And also, currently the generation of the sound takes 10 seconds or 15 seconds. But if we keep improving on the entire pipeline and use better GPUs, have more computing resources, we can potentially make it semi-real time. And in that case, people basically just do whatever they want, and the AR environment will feed them back with the sound effects that matches their actions.
Thank you.
Thank you.
Great, thank you, John. Let's give him a round of applause.